Let's take a look at some problems from your lab assignment in section 11.7. These are strategies for testing convergence. And I wanted to invite you to go to our website, our Canvas site, and under section 11.7, we have the overview, the lab problems, the assignments, and there's this thing called check this out. Check this out. There's a flowchart here that you can download. It's a JPEG. It's an image shot. You can right-click and save as the image, or you can click and drag it to your desktop or somewhere else. But here's the flowchart here. This is a flowchart that I created a while back, and it kind of gives an idea of what to do when you're in the series. It has a decision tree, and it leads you to a few tests that you might be able to use. So let's see how this could be used. Well, let's go over the flowchart first. The first thing it's asking you is that if it's a series that you know. Now we have to commit to knowing a handful of series. The geometric series is especially a big deal for us. There's a P series that we're going to use a lot for testing or comparing. A very special series called telescoping sum was covered, and so if you have any of those types of series, you can quickly assess whether they converge or diverge, and it looks like they would be converging absolutely or diverging. Now, if you don't know the series, the very first test you should try is a divergence test. This is a quick test where you could take a look at the a sub nth term and see if that limit goes to 0 or not. If it doesn't go to 0, then you're done. It diverges. If it does go to 0, you actually have no conclusion, and then you carry out a few other tests or another test to see. So, what are the other tests? Well, if you can integrate it, you do the integral test. If it looks like something that you know, very close to it, but not exactly, then you could do a limit comparison test or a regular comparison test. And then if it contains a factorial, a power, or anything like that, you might be interested in using the ratio test or the root test. And the ratio test and root test has these possibilities. If your limit is less than 1, you converge. If it's bigger than 1, you diverge. And if it's equal to 1, you have no conclusion, in which case you got to try again. So you got to try again, and the ratio test and root test give the same result. So if that didn't pass, then you would just either integrate or comparison test. If it diverges, then you still might have a chance of it converging if it is an alternating series test. So if it's an alternating series. If it is an alternating series, you take the alternating series test, you check if it converges, and if it does, this is the only time you would call it conditionally convergent. If it doesn't converge, and it diverges. And then some other really rare cases, or more like cases that we're not going to cover, if your alternating series, if it's not an alternating series and it's not all positive terms, there still might be a chance for it to converge, but we're not going to look at that. All right, so that's the layout of the chart. Let's take a look at a couple of problems here. Here is the first series. We should determine whether the series converges or diverges. In this case, if I look at this series, I'm looking at the same power for the numerator as it is for the denominator. It's a rational function. We got polynomials on top and the bottom, and they're both linear. And so I know that the limit as n goes off to infinity of this thing will be the coefficients of the highest powers, highest matching powers. So that's 1/2. So an the limit as n goes off to infinity of an is 1/2, and that's not equal to 0. So according to the divergence test, if it's not equal to 0, then you're done, because this thing diverges. So there's a test for divergence there. Alright, let's take a look at the next one. The next one looks complicated, but it's not quite a polynomial over a polynomial because we have a radical sign up on top. But this radical sign is kind of like n to the third power raised to the 1/2 power. So it's n to the 3/2 up in the numerator. And then we have n to the third in the denominator. So this is none of these. It's not a p-series. It's not a geometric series. If you do the divergence test, the power in the numerator is less than the power in the denominator. So the limit's going to be equal to 0, and so it's going to have to be one of these things. I would not use the ratio test for this. You can, I suppose, but I think when you have something that's a polynomial over a polynomial, or something that's close to a polynomial, then I would do a comparison test. And what I would do is I would take the highest power in the numerator. I'll call that n to the 3/2, and the highest power in the denominator is just n to the third power. So we will compare this, use a comparison test, and then you can do the limit comparison test. I think it'll be easier, and then you would compare it to n to the 3/2 divided by n to the third, and so you would add the powers or subtract them, or however you want to look at it. If I were to add the powers or subtract them, I would get 3/2 minus 3. That would be 6/2. That would give me 3/2 negative. Uh-oh, can't see what I'm writing here. So that would give me 4 n raised to the 3/2 power. Let's see if that worked out. Oops, this should be an n. There you go. So that would be my comparison test. This is a p-series. A p-series has a p bigger than 1, and my series converges here. And so if I compare it to my original series, and I have my limit is not 0 or infinity, then it's going to do the same thing, which means it's going to converge. All right, so that's all they're asking for, and that's a limit comparison test. This one looks like something that we can, if you look back in your techniques of integration, we have an e raised to some power and then another polynomial. The power happens to be something with an n to the 5th, and thinking ahead, the derivative of n to the 5th is something with n to the 4th in it. So I think I can simply use an integral test and have it cancel after I do a u substitution. So this, by the way, is none of these series that you know. If you do the divergence test, you can take the limit of this, and using L'Hopital's rule, this is going to go to 0, which is going to give us no conclusion. And then so we do one of these tests, and it looks like something we can integrate. Apparently, you can also use a ratio test for this, so that'll work out as well. Okay, the next one looks like something that it's a polynomial over a polynomial. So it looks like if you were to go through this process, you would see that it's not quite any of these series that you know. The numerator, the power in the denominator is bigger than the numerator, so it's going to go to 0. So a divergence test is going to fail. And then now it's not something I would easily integrate, but it looks like I can do a comparison test. So a comparison test, I would probably do a comparison test n to the 3rd divided by n to the 5th, so that would be 1 over n to the 2nd power. which is going to converge if you do the comparison test. So I think this series is going to absolutely converge. But they talk about doing an alternating series test for this because we have an alternating series. I would really only go to the alternating series test option after this thing happened to have diverged. And so if the power was n to the fourth divided by n to the fifth, then the comparison test would be 1 over n, which is the harmonic series, which is gonna diverge, and then I would do the alternating series test after that. In this case, we have this thing's gonna absolutely converge, but they just want us to use alternating series test. All right. Now the next one that follows is 2 to the k over k factorial, and so k factorial, it's kind of tricky to know what the difference is between an exponential function and a factorial function. And if you do it once or twice, you can see that one of them is going to dominate, so you should be able to tell whether this thing, the divergence test, is going to lead you to infinity or 0. But if you don't know that, you can go down here. It does contain a factorial, and it's some constant to the end. So I'd probably take the ratio test for this. So doing the ratio test will allow you to figure out whether this thing converges or diverges. And you'll see that I think the exponential is going to go faster than the factorial. And then finally we have something like this. This is close to a geometric series, so it's not quite a geometric series. But if it's close enough to a geometric series, then you would probably, it's something that you know. So I would probably do some sort of comparison test, whether it's a direct comparison test or a limit comparison test. All right. So there's a lot of ways to approach some of these. I think if you follow the flow chart here as you try to tackle some of the problems that you guys are doing, then you might be able to get used to some of these tests, get to know some of these tests a little bit closer. And aside from this flow chart, it might be good to have the details of the P series, the geometric series, the telescoping sum. Write that out on a piece of paper, and then write out the divergence test, and maybe give yourself an example. Write out the integral test. There's 2 kinds of comparison tests. There's a comparison test, and then there's a limit comparison test. And if you write those out and find a couple of examples, that would be useful. The ratio test is used a lot. The root test is not used so much, but it comes in a special case when your whole a sub n looks like it's something raised to the nth power. You can do the root test for that. And then write out the text and details for the alternating series test. And then if you have that in front of you as you're doing these problems, then you don't have to worry about flipping through the textbook and finding the details, because you would have written it out. Okay, so I hope this helps, and good luck.